Welcome to the Cables and Connectivity module. This module will cover the features and benefits of cable and connector solutions. Cables are referred to as communications media. Metal wires and glass fibers are the most common media types in today's cabling. It is possible to make cables with carbon or conductive plastic cores, but you are unlikely to encounter these more exotic types. An important role of cable design is to contain the communication signals within these media and protect them from interference. To this end, most cables have coated or insulated media contained within a protective sheath. Cables are classified by the type of media they include, usually copper, single-mode optical fiber, or multi-mode optical fiber. Their construction, for example, unshielded twisted pair, shielded twisted pair, and so on. Their application, horizontal links, backbones, outside or inside, and so on. The most fundamental difference is in how they carry or propagate signals. In cables with metallic media, the signals are propagated by the interaction of electrons in the metal atoms. In optical fiber cables, signals move through the glass through the movement of photons, which we can think of as light waves. The most common type of communications cable is the twisted pair. This usually consists of two strands of copper wire measuring between 22 and 24 on the American wire gauge, which are insulated and twisted together. The twist is vital to their performance. The two wires follow helical paths with opposite directions of rotation. This allows any stray signals induced in the conductors to cancel each other out. So the transmitted signal entering one end of the cable arrives at the receiver without being distorted by stray signals. Most cables contain more than one twisted pair within a common jacket. You will see several types of twisted pair cables used in communications networks. The unshielded twisted pair, or UTP, is the most versatile and common type. Foil twisted pair, FUTP, also known as screened twisted pair, has an aluminum foil shield over all four pairs plus a drain wire. The foil is intended to capture any stray signals entering the cable along its length and drain them to earth. Shielded twisted pair, SFTP or FFTP, has individually screened pairs plus an overall shield. Like the foil in FTP, the shield is designed to prevent electromagnetic interference from distorting signals in the cable's central conductors. The foil and shielding are intended to give extra protection from interference above that given by the error cancellation effect of the twisted pair itself. The twist of the pairs in high-performance twisted pair cables must be maintained during termination. All connectorization techniques require that the twist be maintained up to the point where the individual wires enter the connector or a piece of equipment. Another point to remember is that while twisted pair connectors are physically interchangeable, one manufacturer's RJ45 style jack fits into another's faceplate, they do vary in termination techniques. The manufacturer's documentation will give the details of this. Twisted pair wiring is designed so that the same wires continuously connect from one end of the system to the other. That is, green to green, orange to orange, and so on, as shown here. In this respect, it is just like electrical wiring. This differs for fiber optic circuits. The other type of cable you will find most often in many kinds of networks uses optical fiber as its transmission medium. Optical fibers are very thin strands of glass, typically 125 microns in diameter. A fiber propagates light within an even smaller diameter central core. A micron is 1/1,000,000th of a meter. Multimode fibers have core diameters of 50 or 62.5 microns that permit light to travel along many paths or nodes. The single-mode fiber's smaller 8 to 9 micron core permits only one path, a single mode. Advances in connector technology have made fiber easier to work with, but it is still more difficult to connectorize than copper cable. However, fiber's low attenuation and superior bandwidth makes it an obvious choice for backbone and campus links. Single-mode cables have the highest performance. and can be used for lengths of 70 kilometers, 43.5 miles, and longer. In fiber optic schemes, signals travel over transmit-receive pairs. The integrity of the transmit and receive signals are maintained by a system of polarity where connector orientation reverses at each end of the pair, as shown here. In a coaxial cable, the central conductor is surrounded by a dielectric that is covered with one or more shields, outer conductor. These may be copper or aluminum tubes, aluminum tape, and/or braided wire. On the outside, the cable is encased in a jacket. The different conductors are used for different types of applications. Coax is designed to conduct low-power analog and digital RF signals. Coax is a proven technology for video. Coax is the cable in cable TV and radio frequency transmission. It offers very good bandwidth and low attenuation. Because of this, some data networks such as ThickNet, ThinNet, and cellular wireless links use coaxial media. A coaxial cable has a center conductor and an outer conductor. F-style and BNC-style coaxial connectors are two popular methods for termination. There are also special connectors for specific coaxial cable types. In all cases, the aim of the connector is to establish low-loss connections between the inner and outer conductors of one cable and those of another. And, of course, the isolation between the inner and outer conductors must be maintained. The two critical factors determining data cable performance are attenuation and bandwidth. Attenuation, also known as insertion loss, is the loss of power as a signal travels along the cable. This dictates the cable's operating distance. It is expressed in decibels dB per unit of distance. Lower numbers are better. Bandwidth is the information carrying capacity of a cable. It is expressed in megahertz for twisted pair and megahertz per kilometer for fiber. Higher numbers are better. Broadly stated, the strength of a signal decreases over distance. Other factors, such as poor connections or splices, or even bends and kinks in cables, can also lead to loss of signal strength. Network speeds are constantly increasing. Years ago, a typical system would have a 100 megabit per second backbone connecting 10 megabit per second horizontal subsystems. Today, multi-gigabit, 1 to 10 gigabits per second backbones support 1000 megabit per second to the desktop. The chart shows where twisted pair and fiber cables fit into the matrix of network speed and distance. Categories 5E, 6, and 6A twisted pair cabling support gigabit systems within TIA recommendations for horizontal channels up to 100 meters, 328 feet. Until the last decade, the TIA operating standard mentioned only 62.5 micron fiber. The standard now supports higher bandwidth 50 micron fibers, permitting faster network traffic over longer distances. Nearly all of the main performance parameters used in cabling standards are expressed using the decibel. The decibel is a comparative measure of power levels applied to signals. Although the decibel is a relative scale, it is often expressed as though it were absolute, with an implied reference signal. It is really just a more convenient way to express large-ranging number ratios. Advances in construction and materials produce twisted pair cables with exceptional bandwidth that deliver high-speed transmission over horizontal distances. To achieve high speeds on twisted pair cables, all four pairs are used to simultaneously transmit and receive full duplex parallel transmission. With all four pairs in use, TIA 568 and IS 11801 has standardized minimum performance values not only for performance within a pair, but among all four pairs. These are near-end crosstalk, or next, is the noise one pair induces into another, measured in dB at the receiver. Higher numbers are better. Equal level far-end crosstalk, LFEXT, is the noise one pair induces into another pair in the same cable, measured in dB at the receiver minus attenuation. Higher numbers are better. This is also referred to as ACR-F, or attenuation to crosstalk ratio far end. Power sum near end crosstalk, PS next, is a computation of the unwanted signal coming from multiple transmitters at the near end into a pair measured at the near end. Higher numbers are better. Power sum equal level far end crosstalk, PSLFext, is a computation of the noise coming from multiple transmitters at the near end into a pair measured at the far end and normalized to the received signal level. Higher numbers are better. This is also referred to as PSACR-F, or power sum attenuation to crosstalk ratio far end. Alien crosstalk, ANext, which is the noise introduced into a twisted pair of a cable from pairs in adjacent cables. Higher numbers are better. Return loss, or RL, is the ratio of the signal reflected back by the cable terminated with a 100 ohm resistance to the transmitted signal. A higher number is better. Propagation delay is the time required for a signal to travel from one end of a pair to the other end. Delay skew is the difference in propagation delay of the two pairs with the most and least delay. All of these parameters are important to signal transmission. Now, let's move on to fiber optic cables. Fiber types get their names from how they handle light and their physical construction. The two types are: multimode means it will accept many modes of light because of its large numerical aperture. It supports both 850 and 1300 nanometer wavelengths. Single mode accepts only one mode of light, the axial mode, and supports both 1300 and 1550 nanometer wavelengths. Both are considered dual wavelength fibers because they support two of the wavelengths used by transmission systems. As with twisted pair, optical fiber performance is affected by bandwidth and attenuation. These are key factors in performance standards. Let's look at bandwidth first. Multimode fibers have core diameters of either 50 or 62.5 microns. They propagate light over two standard wavelengths, 850 and 1300 nanometers. Light travels down multiple pathways or modes as described earlier in a multimode fiber. A 62.5 micron core has about 1,100 possible modes at 850 nanometers. A 50 micron core has around 300. The higher the number of modes, the greater the modal dispersion. That is when light pulses spread out and become unrecognizable by the receiver as individual pulses. This is a key factor determining the effective bandwidth of a multimode fiber. Attenuation is the other major factor determining fiber transmission performance. Regardless of how dispersion and other factors are controlled, the light pulse will lose power over distance. TIA specifies that a standard-grade multimode fiber operating at the 850 nanometer wavelength will have an attenuation no worse than 3.5 dB per kilometer and no worse than 1.5 dB per kilometer operating at the 1300 nanometer wavelength. Single-mode fiber has much lower attenuation. The TIA specifies that a standard-grade single-mode fiber operating at 1310 or 1550 nanometers has a maximum attenuation of 0.50 dB per kilometer, 1.0 dB per kilometer if tight buffered. Single-mode fiber is a step-index fiber where the axial mode is transported through a small core diameter 7 to 10 microns. This eliminates modal dispersion. Single mode is used for higher data rate and longer distance requirements and commonly used for long-distance telecommunications links. Standard single-mode fiber is optimized for performance with light of 1310 nanometer wavelength, which gives minimum dispersion. Non-zero dispersion fiber is optimized for performance between 1530 and 1565 nanometers. Some long-haul systems use this single-mode fiber at 1550 nanometers. Optical fibers consist of a germanium-doped silica or glass core within a concentric layer of silica cladding that is 125 microns in diameter. So the glass core through which the light signals pass is surrounded by a glass cladding that tends to reflect back the light waves into the core as shown here. The core and cladding are covered by 2 or 3 concentric layers of acrylate coatings which provide physical protection. The outer acrylate layer is typically colored for identification. The coated fiber diameter is approximately 250 microns. In addition to the 2 main types of fiber, single-mode and multi-mode, there are also 2 main types of fiber cable construction, loose tube and tight buffered. This illustration shows the loose tube and tight buffered cable designs. In the tight buffered type, the protective tube or buffer holds the fibers inside close together, giving them little freedom to move in relation to each other or the buffer. There are 2 variants of the loose tube design. These are the stranded type and the central tube type. This shows the design detail of a multi-fiber tight buffered cable. Strength elements can either be glass-reinforced plastic rods at the center or a sleeve made of aramid yarn located under the outer jacket. Because there is no water absorption gel or powder, the cable is clean to work with. Coaxial cable is composed of a central conductor, a dielectric, a metallic shield, and an outer jacket. Center conductors in coaxial cables are either solid or stranded wire. Solid conductors are described by their diameter and material, while stranded conductors include their stranding. The conductor material can be bare copper, silvered copper, tinned copper, copper-clad aluminum, or copper-covered steel. Most CommScope coaxial cables have foamed dielectrics for better transmission characteristics. Different materials are used to meet electrical and fire safety performance. Some dielectric examples are foamed polyethylene, solid polyethylene. Coaxial shields, also called the outer conductor, come in several varieties. These include foil, where aluminum is bonded to both sides of a polypropylene or polyester tape to provide 100% coverage, and braid, where flexible wire is woven around the dielectric. At a minimum, a dual braid or foil shield is required. A quad shield may be needed for environments where EMI is unusually high. Coaxial cable is in effect a waveguide. It efficiently channels radio frequencies and is capable of carrying hundreds of different frequencies simultaneously. This makes it an ideal media for video transmission and for linking to satellite and microwave dishes. Coax is also used to transport signals between the radio transceivers and antennas that power wireless networks. While coaxial cable was once the media of choice for data networking because it combines low attenuation and excellent protection from RF interference, it has been superseded by twisted pair and fiber optic cables. However, it is still the medium of choice for video distribution, antenna systems for wireless networks, and for some data center applications. Impedance is the resistance to alternating current flow measured in ohms. The nominal impedance of the transmitter, receiver, and cable must match precisely for a system to work at maximum efficiency. An incorrect match will produce a poor return loss situation. Video coaxial cables have an impedance of 75 ohms. Impedance values of 50 ohms and 93 ohms are available for other applications such as antenna or data cables. Attenuation is a limiting factor for coaxial cable, especially at higher frequencies. Attenuation is specified in dB per 100 feet for a specific frequency. Cables with thicker center conductors tend to have lower attenuation. When specifying coax, look for the lowest possible attenuation for the intended operating frequencies. Another performance factor is the velocity of propagation, or VP, or how close to the speed of light the signal travels through the conductor. Nominal velocity of propagation, or NVP, is the relationship of how fast the electrons travel through the conductor compared to the speed of light. Higher numbers are better. CommScope video coax generally uses a foamed dielectric material that significantly increases the NVP. Return loss is the ratio of the power of the outgoing signal to the power of the reflected signal expressed in dB. Structural return loss is the measure of power loss in a cable caused by discontinuities in the cable conductor or dielectric. If these discontinuities are regularly spaced along a cable, they can cause severe transmission losses for frequencies whose wavelengths are fractional proportions of the distance between these discontinuities. Lower numbers are better in both cases. Fire safety is as important as cable performance. This chart shows cable ratings or listings for appropriate sections of the U.S. National Electrical Code, NEC, and the Canadian Electrical Code, CEC. Plenum cables are listed for use in plenum spaces. Riser cables are used in building risers, raceways, and trays. NEC Article 770 covers fiber optic cables. Article 800 covers communication cables. Article 725 covers signal, remote control, and closed-circuit video cables. Article 760 covers cables used in fire protection signaling, and Article 820 covers cables for television. It is important to know that local codes may supersede NEC regulations. For instance, some local fire codes require the use of plenum cables in risers. In all cases, obey local codes. Here is a diagram showing which codes apply to which parts of the cabling infrastructure. Remember, you can always substitute a higher for a lower, but you can never substitute a lower for a higher. That completes the Cable and Connectivity module. Thank you.